Hi folks. So we've been talking about galaxies and the different types of galaxies and how to categorize those galaxies. We've talked about spirals, ellipticals, and irregulars. But about 1/4, about 25% of the galaxies that are out there don't fall neatly into these categories. There's some weird things about them. They may look like a standard galaxy, but when we look at them, they've got emission, they're putting out energy that's way more than just what could be coming from the stars. So these are called active galaxies, and that's what we're going to look at today. So let's get started. All right, so as always, make sure that you got your active galaxies tool out. Looks like this. These are your class notes. Also, go ahead and have out the practice sheet because I'll be talking about this here at the end of it, just to kind of give you a few tips as to where to go with that. So pause the video until you're ready to go. All right, so as I said, about 1/4 of these galaxies don't give out the kind of light, they don't have the kind of spectrum that we would expect from a normal galaxy. Here's, looking at the purple line here, this is a normal galaxy, and you see that most of the light is coming from the visible. Well, that's because it's coming from stars. Stars put out most of their light in visible. They put out a little bit in infrared, they put out a little bit of radio, but practically all the light that we're getting is coming in the visible range. When we look at these strange galaxies, these active galaxies though, we see that we get pretty much the same amount of energy throughout the spectrum. And not only is it being more evenly distributed throughout the spectrum, but there's a whole lot more of it. So something is going on with this that is not being produced by normal stars. And so we call this non-stellar emission because it's not being produced by stars. So we're going to talk about three types, and I'll give you a little spoiler. It turns out they're all going to be basically powered by the same thing, but just to give you an idea of where we're coming from. This is called a Seyfert galaxy, and the core of this, if you look at the core of it, is much more luminous. This is a spiral galaxy, and you can see that the core is, a significant fraction of the whole galaxy, but it's much brighter than it should be. Also, though, when we look at it in radio, it's putting out a whole lot of radio emission in addition to X-rays and infrared and some of the other wavelengths that are out there. So something is making this galaxy much brighter than could be accounted for just by the stars. When we look in the center of the galaxy, we see that there is very rapid variation in the core. Well, think about it. Things can only propagate at the speed of light. So if I have something that's 1,000 light years across, there's no way that I could get a change on this side to propagate all the way through in less than 1,000 years. But when we look at this, we're seeing changes over the course of just 2 or 3 years. See, this flare right here was in 1980 and then coming down here in about 1983. So that means that this, whatever is producing the energy that's powering it, must be very small. What you're going to be doing in your practice is you're actually going to be calculating how small that actually is. Second type is radio galaxies. This happens to be Centaurus A. And this is the closest active galaxy to Earth at 3 million parsecs away. When we look invisible, this is all we see. And there's this bright energy here, but this dark area is dust lanes in the disk of the galaxy. And then coming out from the center, up and down from the center, we've got this huge amounts of material that's being streaming out of the galaxy. And that material itself is radiating radio waves from that. And so that's what we call these radio lobes that you see here. So this is actual material that's being thrown out of the galaxy and with a lot of energy as well. This is in X-ray, and we see that that material is also emitting X-ray. We're looking at, it's basically the same shape. So this is the same stuff, the same gas, dust, whatever it is, that's emitting that, but you don't see that in the visible range. We think that Seyfert galaxies and radio galaxies are the same type. So here's my galaxy, and remember that the disk of the galaxy is going this way. So, well, oriented on the camera, it's going to be like this. But the lobes then are coming out of the face of the disk. So core-dominated galaxies, they have their disk oriented face on. I'm looking straight down this way, so I don't see the lobes coming out. Instead, I just see this bright point. Well, actually, that bright point is the lobe as it's pointed towards Earth. On the other hand, if I happen to be oriented so that I'm looking this way, now I'm looking at the galaxy edge on, and because remember, my disk is going this way, so I'm looking at the galaxy edge on, and now I can actually see the lobes coming out. So lobe-dominated galaxies and core-dominated galaxies are the same thing. It just matters on how we happen to be oriented relative to the galaxy. quasars are the last one that we're going to talk about, the third one that we're going to talk about. And this is showing the quasar QC273, which is the closest one to Earth, 680 million parsecs away. And it's a good thing it's that far away because these things are incredibly bright. And I make a note here, I mean, it appears to be just a star and not even a particularly bright star. But when we looked at this, the spectrum from it was actually very odd. And so this would be the normal rest spectrum here for a star. And you see we've got the hydrogen lines here that we're used to dealing with, hydrogen, beta, gamma, delta. Those are those red, blue, and purple lines that we've been working with. But when we looked at this, we thought, wow, there are some elements in here that we just don't know what they are because there's nothing that matches up. Only later did we realize that it was an extremely strong redshift. So like a redshift that we don't see normally anywhere else in our galaxy or really even in the universe from that. We're going to learn when we study Hubble's law in another week or so that what's happening is space is expanding. And so that redshift, the galaxies moving away from us, gives us a measure of how far away these things are. And it turns out because of this extreme redshift, these things are crazy far away. And yet they're still bright even from Earth. That means that they must be putting out an immense amount of energy for them to still seem that bright. So this is a Hubble Space Telescope imaging the core of the galaxies, and it can actually see in the center these really bright spots. So we now know that the energy from these quasars, like we see right here, that's actually a galaxy. It's not a star. And so that energy is coming from the core in the same way that the radio and the Seyfert galaxies are producing their energy. So something's got to be powering them. So we know whatever these things have a high luminosity. We know that their energy is not coming from stars. It's a non-stellar energy source. We also know that it varies very quickly and it's coming from the core, and that core must be really small. Finally, we also get explosive activity. So it's not just continually radiating. We'll get these flares, these bursts of energy coming out from these things. So the only object that we can think of that meets all of those criteria is a supermassive black hole. And so this would be the black hole in the center of the particular galaxy. It's just so big that as that material, that gas and dust falls in, then it's giving up its gravitational potential energy. Well, if we look here, there's still the disk of the galaxy. So that energy that's coming out here gets radiated, and it's going to be fairly, short wavelength, high energy stuff. However, those X-rays and gamma rays get reprocessed by the disk. It gets absorbed and then re-emitted as radio and infrared. So this is why we're getting this basically flat spectrum where we're seeing everything instead of seeing mostly just the star-like emission coming from that. So it's the energy is being generated here, and then it's kind of being changed into all of the different forms because it's being absorbed and re-emitted by that dust. So we find that the radio galaxies and Seyfert galaxies are, like we said, more than 3 million parsecs away. There are not any in our local area. And then quasars are even further than that, 680 megaparsecs to all the way out towards the edge of the universe. So remember that as we look out into space, we're looking back in time because it takes that light that much time to actually reach us. So if something's 680 million parsecs away, you're seeing the universe as it was 680 million years ago. And we can see that further and further back. So we find that the normal galaxies, like the Milky Way, for example, they seem to have used up their core, all the gas in their core, and so they're not lighting up. That's the modern day galaxies. Radio galaxies, we're moving back in time. The gas is just beginning to get used up, so it's less luminous, and then moving back in time even further. Quasars then are these young galaxies where we've still got lots of gas and dust left. So we can see that working backwards. Now let's play it forwards. So we have these early galaxies that are created, and there's a lot of gas and dust in them. They've also got this supermassive black hole in the middle. As that gas and dust spirals down into the hole, it gives off energy. So the quasars are going to be very bright. But as that starts to age, that same galaxy, as it starts to age, so we're seeing the ones closer to us, as it starts to age, then it's got less of that gas, and so it's less energetic. And that's what, at this point, it's going to be considered to be a radio galaxy. When it's finally come up to the normal range, the modern period, then it's used up pretty much all of its gas and dust. And so it's never going to be that luminous anymore. Now, we think that the Milky Way probably didn't start out with enough gas and dust to ever have been an active galaxy. So this certainly wouldn't be true for all of them. But it explains why, a good percentage, about 25% are. All right, so one of the things that we can do is we can get a theoretical maximum mass, an upper limit to the mass, for using what's called the Eddington mass. And so this is something that's going to be new. So you guys know that there's a relationship between absolute magnitude and luminosity. They're basically the same thing. They're both just measuring how bright, how much energy this thing is putting out. So if I know the absolute magnitude, then I should be able to get the luminosity directly. I shouldn't have to have the flux from Earth. And so that's what this formula right here is showing you, is that L is 10, and this is raised to the power, and then the fraction 4.8 minus m divided by 2.5. So make sure, if you're typing this in all at once, make sure that you've got this whole thing in parentheses. So kind of two sets of parentheses with this. What I suggest you do, work out that fraction first. Take the absolute magnitude. M here is not the mass, it's the absolute magnitude. Do 4.8 minus the absolute magnitude, hit equals, divide by 2.5, and then you've probably got an anti-log or a 10 to the x button like we used last time. Just hit that, you're going to be good to go. Once I know the luminosity, then I can use the Eddington mass. You just divide that luminosity by 3.2 times 10 to the fourth, and that gives you the maximum mass that object could be. The actual mass is going to be quite a bit smaller than that. But this is the theoretical maximum. And what we find then, if that theoretical maximum is still small, then we know that we're probably going to have, or at least we know that this is as big as it can possibly get from that. All right, so finding the absolute magnitude, if you know the distance, then you can find the absolute magnitude. And we did this in a tool a little while ago. So here's the distance modulus. We want to solve this for m. So I'm going to multiply both sides by 5 and subtract the m, and we get this. So this is the format. If I know the apparent magnitude and I know the distance, then I can get the absolute magnitude. And then if I've got the absolute magnitude, I can get the luminosity. And if I've got the luminosity, well, then I can get a theoretical mass for it. You're going to use this in lab, so that's why we're presenting this. So it might be worthwhile while you're doing the lab to come back to the video and make sure that you review that. All right, before we sign out though, I want to talk about the practice worksheet just a little bit. You'll notice on the practice worksheet that there's a flare that's showing you there, and it says on what day did it begin and what day did it end. So you take the flare and you just find the first day, find the day when that flare begins and the day when the flare ends, and then you'll end up just subtracting them. Then that's in light days. That tells the size in light days, because that tells it's moving at the speed of light. And so if it takes, 5 days, whatever it is, then it's the object is 5 light days across. What we want you to do then is to convert that into astronomical units. And the conversions that you need are down here at the bottom. So you'll find, just subtract the days between the flare. That tells you the number of light days across the object producing the flare is. And then convert that into kilometers using the conversion here. And then once you've got it in kilometers, use the conversion here to convert it into astronomical units. Okay? And then don't forget to do the final question. All right? If you've got any questions, always come by Live Help. That's what I'm here for. Okay, so now we know that because of the size of this flare is so small and because it's so energetic, we know that probably this is in fact quasars are being powered by a supermassive black hole. And so you're going to do, when you get into the lab, you'll actually look at that more in detail. And of course, with the practice, you can actually calculate the size of that. But keep in mind that these are the galaxies that occurred in the past. And as they've evolved, we see fewer and fewer of these. And that's a really good thing, because these things are putting out so much energy, you can imagine them sterilizing everything that's in that particular galaxy. So having the fact that we don't have one of these close is actually a really good thing. All right, so that's it for this time. Go through the lab, and as always, come see me if you have any questions. We'll see you next time.